you already know, a field is the changed space around an object. For example, the gravitational field is the changed space around any object that has mass. An electric field is the changed space around any object that has electric charge. A magnetic field is the changed space around a magnet. Now, the gravitational field acts on things that have mass. If you have mass, you'll create a gravitational field and be influenced by a gravitational field. The electric field influences charges. It's created by electric charge, and it influences electric charge. A magnetic field is created by a magnet, and it affects magnets, and also, and this is particularly strange, moving electric charges. That's pretty interesting. A moving electric charge is affected by a magnet, but a stationary one is not. If you'd like to know more detail about that and to why that is true, you'll have to take AP Physics 2 and learn a little bit about special relativity. We can detect magnetic fields pretty easily. If you have a magnet and you take, say, a little device that is another magnet, then it comes near it. Here, let me get closer. You can take this magnetic field and you can actually see the direction the magnetic field is facing. You have these lines that are spraying out almost like a fountain from this magnet, and it is in 3D. I can come back, I can come forward. And it's like they come up and out. They're straight up above the magnet, and then they come out, and then they curve and go downward. And so that is a pretty neat thing. The magnetic field is invisible, but we can render it visible if we have a tiny magnet. How about if we have a lot of tiny magnets, say a bunch of iron filings? We can sprinkle iron filings onto a magnet. Ideally, without creating a mess, you have a barrier in the way. Sprinkle them on and you can actually see the field. And that's a pretty neat thing too. This has some similarities to electric field in that, say, for example, where the field lines are super close together, you have a stronger field, and where they're more spread out, you have a weaker field. So one of the really big differences about magnetic fields versus electric fields is what they do. Magnetic fields actually put forces on charged particles. So we represent a magnetic field by the letter capital B, and we sometimes call them B fields. The unit for a B field is, well, we'll get there. So first things first, what a magnet does to a charged particle depends on the magnitude and the sign of the charge. It'll affect positive charges one way, negative charges the other way, similar to electricity. The stronger the charge, the more it'll get affected. The stronger the magnet, the more it will affect the charge as well. But it also depends on the speed of the charge. The faster the charge is going, the stronger a magnetic effect it feels, the stronger a force. And so there you have it again, that relationship between magnetic field and velocity. That's particularly strange if you imagine different reference frames. If you're holding a magnet and you have a charged particle and you run with them, the charged particle won't be affected by the magnet because the charged particle isn't moving with respect to the magnet. But another charged particle identical to it that you run past, that charged particle will be affected by the magnet because they have relative motion. Strange. It also depends on the angle between the magnetic field and the charged particle. If the charged particle is moving with a magnetic field line, it experiences zero force. If it is moving perpendicular to a magnetic field, it feels a maximum force, and interestingly, the force is perpendicular to both. It's orthogonal. Strange, very strange. So anyway, if we put all this together, we end up with an equation for the force that a charged particle feels because of a magnetic field. We have FB equals QVB sine theta. Q is charge, V is velocity, B is the magnetic field strength, theta is the angle between them. Maximum at 90, minimum at 0. Interestingly, if you have a wire and you run electricity through the wire while it's between a magnet, it will jump. It will experience a force. And QVB is the same thing as BIL. You have velocity of charge, you have flow of charge. You can convert those very easily. And if you want to do that for extra credit, I'll probably let you. QVB sine theta or BIL sine theta if you're dealing with a wire rather than a particle. If we solve that equation for magnetic field, we end up with force divided by QV sine theta. And sine theta doesn't have any units. Force is newtons, charge is coulombs. You get meters per second for velocity. So you end up with a Newton per coulomb meter per second, or a Newton per amp meter? That's quite a mouthful, isn't it? We decided to name the unit of the magnetic field after Nikola Tesla for all of his contributions to electromagnetism, and so we call the unit of the magnetic field the Tesla. In the UK, they will often use a Gauss. The Gauss is 1/10,000th of a Tesla. And so it's CGS, centimeter gram seconds metric system, rather than MKS, meters kilogram seconds. A Gauss and a Tesla are almost the same thing. A Gauss is 1/10,000th of a Tesla, but they are both metric units. Magnets can range, say, from 0 up to maybe 5 Tesla for a very strong permanent magnet. The strongest electromagnets we've ever created in particle accelerators go up to about 30 Tesla, whereas the magnetic field of the Earth is about half a Gauss. That's 0.5 times 10 to the minus 4 Tesla. It's really weak. It is also very, very big and does a good job shielding us from a bunch of cosmic rays as well as a bunch of the solar wind from the sun. The sun distorts our magnetic field a lot. It doesn't so much look like a bar magnet, which is in a lot of pictures, as a bar magnet that has been stretched like taffy. But yes, so the Earth's magnetic field, the geosphere, is really, really big, but also very weak. In our next video, we're going to talk about electromagnetism and how we can use electricity to create magnetic fields of various shapes.